All right, folks, welcome. This is the nuclear chemistry review packet. And make sure you've got a calculator, make sure you've got your reference tables opened up to page 6, which is table N, and then on table O on page 7, we're also going to need that, and maybe a scrap sheet of paper or the side of this, so either one. Okay, so the nucleus of a radium-226 atom is unstable, which causes the nucleus to spontaneously decay. So that's what it means to break down. By the way, this is the mass number. So 226, radium-226. It will not absorb electrons. If it absorbed protons, it would change from radium. Oxidized means the loss of electrons, so decay. Which list of nuclear emissions is arranged in order from least penetrating to greatest? This is directly from the notes. So I like to think of it as alphabetical. So alpha is the weakest, beta is a little stronger, and gamma is the strongest. Which nuclear emission has the greatest mass? So remember, if we have a mystery particle, whatever is up here is the mass, whatever is down there is number of protons. So we should go to table O. Alpha particle, if you look, that's 4 over 2 He, or 4 over 2 alpha symbol. Beta is 0 over negative 1 B, or the little e for electron. Gamma is the 0 over 0, and positron is 0 over plus 1 E, or the B with the tail. So mass is up here. So which of those has the greatest mass? It is choice 1, the alpha. Okay, decay reactions, decay equations. What is the mystery particle? Remember, we need to follow law of conservation of mass. So total masses on both sides must be the same. Total number of protons on both sides must be the same. So 6 and 4 gives you a mass of 10. 1 plus blank has to give you 10. 9. So I'm going to do it over here to make it bigger. 9. 3 plus 2 is 5. 1 plus blank is 5. 4. So 9 over 4. Well, unfortunately, 2 of these say 9 over 4. So how do I know which is the correct answer? Let's go to reference table. Who is atomic number 4? That's beryllium. So they're trying to trick you here. Beryllium is the answer. When radium-226 undergoes natural transmutation, it emits. So remember, natural transmutation is spitting out of particles and energy all by itself. How would I know that? That doesn't sound like something I need to memorize. So let's go to reference table N. I find radium-226. Decay mode is alpha. Just look that right up. Which reaction represents natural decay? So some of these are not nuclear reactions. Some of these are just chemical reactions. So let's get rid of anything that doesn't have the isotope notation. So that isn't and that isn't. And also nuclear decay means changing. So we need to see a change in the actual elements. Okay. So natural decay happens on its own. Sorry, super messy. I'm working on getting that optical mouse. So who is breaking down on their own? That is uranium-235. Choice 3. This is natural. This is called artificial transmutation. Nitrogen-14 is stable. It doesn't want to break down. It doesn't want to decay into something else unless you bombard it with one of these. And what is that? That's an alpha particle. Again, what is an example of natural transmutation? This is one reactant breaking down all by itself. So can't be this one, can't be this one, can't be this one, because I see 2 reactants. So one reactant all by itself spitting out this, which is an alpha. If I didn't know that, it's on table O, and it's decaying into uranium-235. Notice I am transmutating. I am changing from one element to another by changing our protons in our nucleus. So that's choice 1. Alpha particle has the same composition as, well, let's go to table O. You find alpha particle is 4 over 2 alpha symbol, or 4 over 2, 2, oh my goodness, sorry, He. So right there, that's your answer. Why is it just a nucleus and not the whole atom? Because there's no electrons. Now, what is a hydrogen nucleus? That would be 1 proton, and this would have 2 over 1. This is a 1 over 1. This is a 2 over 1. And beryllium, that doesn't even matter. That's 4. When an alpha particle is emitted by an atom, atomic number will. Okay, well, let's figure out somebody who does that. Let's go to table N, and we see that radium-226. Radium-220. Well, I could have chosen any of the alphas on table N. Where's radium-226? Okay, so radium-226, Ra. I know that's going to give off an alpha because it told me, and because the question says so on table N. So what is the number of protons for radium? I have to look that up. Honestly, I do, because I don't have this memorized, and there's no shame in that. So radium is 88 protons. All right, let's see what happens. Use conservation. 226 equals 4 plus blank. 222. Got to follow law of conservation. 88 equals 2 plus blank. 86. And 86 is, I believe, radon. It is. So what happened to the atomic number? It went from 88 to 86. Decrease by 2. Okay. Number 10. Diagram. The diagram below represents radioactive emanations, things that are given off passing through an electric field. So we have a lead block giving off some kind of a radioactive source. Looks like arrow number 1 is attracted to a positive plate. Arrow number 2 travels directly through. Arrow number 3 goes towards the negative plate. What kind of emanation is going to be represented by arrow number 1? What would be attracted to something positive? How about something negative? So who is negative? How do you know? Table O might help. It's a beta. Now, who would be attracted to a negative plate? Something positive like an alpha or a positron? Who would not be attracted to either one of these? Neutron, gamma radiation. So remember, opposite charges attract. And so that's what this one is getting at. Which 2 radioisotopes have the same decay mode? So I'm going to take a look at table N. Calcium-37 is positron. Iron-53 is also positron. So I'm guessing that's going to be my answer. Let's just double check. Francium-220 is an alpha. Cobalt-60 is beta, so that's not it. Potassium-37 is a positron, and this is a beta? Nope. By the way, we need table N. Technetium-99 is beta, and neon-19 is positron, so I was correct with that. Which is correctly paired with the notation of its emission particle. Calcium-37 is positron. This is alpha. That's not it. Uranium-235 is alpha. This is positron. How do I know this? So this I need table N. This I need table O. So nitrogen-16 on table N, it says beta. This on table O is a proton. That's not it. Hydrogen-3, which is called tritium. Where are you? It is beta. Table O, that's beta. Positrons are spontaneously emitted from which? This is K37. That's our answer. Let's just double check. Radium-226, that's an alpha. Nitrogen-16 is a beta, and thorium-232 is an alpha. So we wanted positron. Which is positron decay? So positron is 0 over positive 1e. So that's not it. That's not it. That's not it. That's it. This is a beta. This is an alpha decay. Oh my goodness. This is beta decay. Excuse me. This is alpha decay. This is natural transmutation. Excuse me. Artificial transmutation giving off neutrons. This is the positron right here. Which equation represents a spontaneous nuclear decay? So that means natural transmutation. Let's get rid of anything that is not nuclear. So this is a chemical reaction. Down here. So both of these are changing from one nucleus to another, but which of them is doing it spontaneously or by themselves? Choice 4. All right, so we need, I'll be quiet. We need table O for this one. What is the difference between alpha and beta? So alpha is 4 over 2 He. Beta is 0 over -1 B. This is also an alpha symbol. So it looks like mass is different. Looks like charge is different. Now I know this is negative. What's the charge of a nucleus? Hey, that's positive. So both mass and charge. When cobalt-60 undergoes nuclear decay, what does it emit? So cobalt-60 on table N is a beta, choice 3. What happens to protons? So let's do it. So potassium, oh my gosh, sorry, it's like carbon, 14N. So how do I know how many protons there are? Periodic table. 6 of these, 7 of these. I guess I could figure out the rest, although I don't really need it for this question. So the protons looks like they go from 6 to 7. That's an increase. An electron is a charge identical to, well, you should know electrons are negative, neutrons are neutral, protons are positive, alphas are nuclei, which is positive, beta. On the old reference table, it used to say on table O, beta particles, parentheses, electrons. Which kind of radiation has neither mass nor charge? Well, it's got to be gamma. How do I know that? On table O, it says 0 over 0. Gamma is pure energy. In the universe, there's matter and there's energy. And so this is energy. These are matter. As a radioactive element emits gamma radiation, what happens to the atomic number? Well, if it's going to have a 0 over 0, there's no change. No change. Okay, now we need some half-life. So calculations, we are going to use our calculators, and I believe we might need some different values than table N in the reference table. I think we have to use the table N on the last page of this because the numbers have slightly changed. If you are using regular table N, that's okay. You're just going to get something a little bit different. You choose whatever's closest. How many days are required for 200 grams of radon-222 to decay to 50 grams? So I'm going to set up my chart. By the way, remember, there's no wrong way to do this. This is just my way. So I see mass, and I see time and days. I know that I start with 200 grams, and I start at time 0, days 0. So let's go from 200 to 50. Remember half-life, we get rid of half. So half of 200 is 100, half of 100 is 50. So let's look for the decay mode, the length of the half-life of radium-222. So looks like on the new reference table N, it's 3.823 days, and this is just 3.82 on the back. So 3.82. Now, that's how long it took for one half-life to happen. 3.82 plus another 3.82 is 7.64. So don't forget to always start at time 0 and add your half-life. You take half and half and half and half of your mass, but you're adding that same time. Based on table N, what fraction would remain unchanged after 56.2 years? So it sounds like we need fraction and we need time in years. Start with time 0. What's a fraction that means the whole thing? How about 1 over 1? Now, we need the half-life of strontium-90, 28.1 years here, strontium-90, 29.1 here. I think I'm going to go with the 28 just because that's what I used, so bear with me here. If you are using the new reference table, your numbers are going to be slightly different, but that's okay. So it's strontium-90, 28.1 years, so it's a fraction that means half, 1 over 2. Okay, so add another 28.1, and you're going to get that 56.2. So what's the fraction? 1/4. According to table N, which radioactive isotope will retain only 1/8 of its original sample after 43 days? So let's see. We've got fraction, and we've got time, which is in days. Fraction, it means 100% is 1 over 1 times 0. Well, we need to go to 1/8. So we need 1/2. We need 1/4. Then we need 1/8. So that's 1, 2, 3 half-lives is 43 days. So using the old reference table N, which is the last page here, gold 198. Where are you? Oh, the first one, 2.69 days. 2.69 plus 2.69 plus 2.69. That is not enough. That's only 8.07 days. That's not it. Iodine 131. That is 8.07. 8.07 plus 8.07 plus 8.07. 24 days and change. Nope. Phosphorus 32. 14.3 plus another 14.3 plus another 14.3. That's 42.9. 42.9 rounds to 43. That's our answer. You could do the same thing with this. Remember, I'm using the old table N. That is the last page of this thing. If you're using the new table N, your numbers are going to be slightly different. 25. Base your answer to the following question on the graph below. The graph represents the decay of radioactive material at X. What is the half-life? Well, this is defining half-life. Half-life means the amount of time for half of the sample to become stable. So it looks like I have 100% here. Where's 50%? Here. So then I come down to the time, and it's 5 times 10 to the third. So 5 times 10 to the third is 5,000. We're looking for the original sample this time. So we have time in days, and we have mass. We're going to work backwards. So instead of starting with time 0, we're going to start at time 40. Instead of mass original, we don't know. We know that there's only 1 gram. So instead of chopping the mass in half, we're going to multiply the mass, double it each time. Instead of adding the half-life, we're going to subtract that half-life out. So according to that old reference table, iodine 131 has a half-life of 8.07 days. So we need to go down all the way to time 0. So 40 minus 8.07 is 31.9. Subtract 8.07 and we get 23.86. Now, while I'm doing this, you might be saying to yourself, that's not how I do it. I don't do it like that. I use a formula or I do something else. I don't really care how you do it. You just need to be able to show some kind of work somehow. And then so that should be 0. So now we just have to keep doubling, doubling, doubling. So 1, 2, 4, 8, 16, 32. There we go. Excellent. All right, 27. What is the half-life? I start at mass of 10. Half would be here. So then the half is 10 is 5. So then I come down. Looks like 30 years. 2. What is the half-life? Okay, so now I need to figure it out. Looks like I start at 40 grams and I need to go down to 5. So 40, half of 40 is 20. Half of 20 is 10. Half of 10 is 5. How many arrows is that? That's 3. 3 changes, 3 half-lives was 30 days. How do I figure out how long 1 half-life is? Looks like it's going to be 10 days. You might be able to do it a different way than me, and that's okay. All right, the half-life of a radioactive isotope is 20 minutes. What is the total amount of a 1 gram sample remaining after an hour? So it looks like we've got time and we've got mass. So we've got mass of 1 gram to start. It starts at time 0. That's important. Don't forget that. So then we have the half-life is 20 minutes. So after 20 minutes, what's half of 1? 0.5. After another 20 minutes, what's half of that? 0.25. After another 20 minutes, that's 60 minutes, which apparently they want you to know that 1 hour is 60 minutes. Hope you do. So that's going to be half of that, which is 0.125. So choice 4. Okay. What is the number of hours required for potassium-42 to undergo 3 half-life periods? This is easy. You don't have to do a chart for this. We just say 3 times the half-life of potassium-42. So according to the new one, it's 12.36. According to the old one, it's 12.4. I'm going to use the 12.4 just because it's probably based on this. 37.2, yeah. You'd get something very similar. What would you get? 12.36 times 3. Yeah, you get 37.08. So you would still know how to round that. The chart below shows the spontaneous nuclear decay. This is the decay series. What is happening? All right, so let's check. The first one, we go from 238 to 234. We go from atomic number 92 to 90. So what's the change? Looks like the change is a 4. The change is a 2. 4 over 2, hey, that's an alpha. So we're going to start with alpha. This is an alpha change. That's supposed to be an alpha sign. Then we go from 234 and remain 234. Notice how that mass does not change. But we went from a 90 to a 91. So that means we've got a 0 change here, and protons, we actually didn't lose any. We gained some. -1, that's beta. So alpha, beta, this is a beta, and there's exactly the same motion where the mass doesn't change but our atomic number increases. So alpha, beta, beta is our answer. Which product of nuclear decay has mass but no charge? So it does have mass, but there's no charge. This is a table O question. This is a neutron. 4 over 2 He, 1 He, 1 over 0, and gamma 0 over 0. Don't get tricked. This doesn't have charge, but it also doesn't have mass. Beta 0 over -1. That doesn't have mass. That does have a negative charge. What is the X? Okay, don't get tricked. There's a 4 here. So 2, I'm going to get my calculator out because come on now. Can't do that kind of math in my head. Maybe you can. It's late. 12 plus 249. And I plugged it in wrong. 249 is 261. And then I have, let's just call it equals, even though it's not, 257 plus 4x. Okay, so let's subtract 257 from both sides. 4 equals 4x. So the mass must be a 1. So that gets rid of those. Let's figure out protons. 98 plus 6 is 104. 104. Sorry, this is messy. 104. And I have 104. So what is this? 1 over 0. Who's a 1 over 0? Table O, if you didn't know, it's a neutron. Okay, another mystery particle. Mass on this side is 10. 9 plus 1 is 10. 3 plus 2 is 5. 4 plus 1 is 5. Who is a 1 over 1? That's a proton. Radioactive cobalt-60 is used in radiation therapy treatment. Cobalt-60 is beta decay. If it's going to undergo a beta decay all by itself, it's called a natural transmutation. Artificial transmutation would have 2 reactants. It would not undergo anything on its own. Fusion, which we'll talk about later, it's small nuclei coming together. Fission is a super large mass of a nucleus being split. So natural is on its own. Artificial means we have 2 reactants. And we're not talking about a really big one being split with a neutron. We're looking for other things. This is very easy because there's only one nuclear choice. These are all chemical reactions, so that's easy. Which statement describes what happens in fission reaction? Fission, this is a straight definition. So in a fission reaction, heavy nuclei split into lighter nuclei. That's our choice. Light nuclei form heavier. This is called fusion. Energy is released and less stable elements are formed. Energy is absorbed. No, that's not the definition. Compared to an ordinary chemical reaction, fission reaction, any nuclear reaction is going to release energy, and it's going to release a lot more. That's why we use nuclear reactions in power plants and in bombs, because we need all that energy. And that's why we don't do those kinds of reactions in a high school lab. We just could not. What happens in an uncontrolled fission reaction? This is like a bomb, nuclear bomb. Mass is created and energy is released, stored, released, stored. Okay, well, first of all, you are giving off energy. So energy must be released. Okay, that's the whole point. You see it, you hear it, you feel it, it's given off. Mass is created. No, mass is converted to energy, which is released. By the way, this is Einstein's equation, E equals mc squared. You don't need to know that. You don't need to calculate it really, but you need to know in a nuclear reaction, mass is converted to energy using that formula. What is x? So 2 plus 3 is 5. 4 plus 1 is already 5, so this must be a 0. 1 plus 1 is 2. 2 plus 0 is 2, so this must be 0 also, which means what is 0 over 0? That must be energy. This is gamma converted from the mass. All right, keep going. Fusion differs from fission. Fusion is bringing together, forming a lighter isotope, forming heavier. We need to form heavier. We don't want more mass, and they both convert mass to energy, so we want this. Fusion, these are small nuclei. What do I mean by small? I mean small mass coming together. This is easy because those are not nuclear reactions. Those are chemical reactions. If you're looking for a nuclear reaction, you should look for isotope notation. These are small nuclei, mass of 2, mass of 3, coming together to form something larger. This is fission. That's uranium-235 bombarded by a neutron, spitting out all these smaller things. Fusion. A serious risk factor associated with the operation of a nuclear power plant. What's the risk? How about waste with a long half-life, hard to get rid of it? What's a problem associated with nuclear power plants? Now, I know this wasn't in the college prep notes necessarily, but I would hope common sense can prevail, and what you've talked about in other classes might come to the fore here. What's a problem? A small quantity of energy is produced. No. Produced acid rain from carbon dioxide? No. It's impossible to control fission. No, it is possible. That's why we do it. It's difficult to dispose of waste. Yes, that's our choice. Okay, now these are just straight up definitions. Thyroid. I-thy. Cobalt-60, I'm sickly. That's cancer. Phosphorus-32, I think that's a tracer. Uranium-238, that's age of rocks. Okay. Medical, if you're putting a radioisotope in your body, do you want it hanging around for the rest of your life or longer? No. You want short half-lives. And do you want it to stay there forever? No, you want it to be quickly eliminated. Pinpointing brain tumors. First of all, carbon-12 is not radioactive. That's our stable isotope. So now we're down to and by the way, so is lead-206. What are we left with? Which is the brain tumor? Technetium, diagnesium. If you don't like my weird ways of remembering, then you should just straight up remember from the notes. This is the brain tumor stuff. Uranium-238, not that. Radioactive isotopes, study of organic reactions. Well, gee, organic, you should have a carbon. Which one of those is used in radioactive? It's got to be carbon-14. Carbon-12 is not radioactive, it's stable. Treating cancer, carbon-14 is dating once living things, dating rocks, decaying into rocks. Cobalt-60, I'm sickly. Radiation used in the processing of food is intended to. Now, why would we radiate something like beef, ground beef? Increase the rate of nutrients. Do we want nutrients to decompose? No. Do we want to kill microorganisms? I think so. Do we want to convert nutrients to stable? Nutrients are stable, darn it. Replace chemical? No. Okay, this is going to be the end of just the regular Regents college prep. If you are in the honors, continue watching. If you are not in the honors and you want to learn something, well, by all means, continue. All right, so nuclear power plant stuff. Which materials are commonly used for shielding in a nuclear fission reaction? Again, these are just straight up definitions. What are going to prevent the reactor from giving off energy to the personnel, the people working there? It's going to be steel and concrete. Water and molten sodium are used in reactions as, now think about it, when something's hot, how can we cool it down? You can put it in some water. You could also put it into sodium metal. So it's a coolant. These are not moderators or fuels. What would a coolant do? Well, absorb energy produced. These are other things. Those other ones are not made up. They're just other things. The diagram below represents a nuclear reactor. The arrows indicate the direction of the flow of water. What is A? Looks like A is near the fuel rods. It is a rod shape itself. It's a control rod. In a fission reactor, the speed of the neutrons, how could you slow down the neutrons? Definitely not an accelerator, not a fuel rod, and not shielding. If you think about it, in a debate, a moderator kind of keeps the flow of the talking. It kind of slows it down if it's getting off course. It helps keep it on course. So use that English context clues to help us here. Which substance is used as a coolant in a reaction? Heavy water. If you don't remember this from the notes, heavy water is H2O. But instead of using the regular, most common isotope of hydrogen with a mass of 1, we use the deuterium isotope of hydrogen, which is a mass of 2, which makes it heavier. Substances used as fuel. What would we need if something is going to be fuel? How about you need to be able to split it to give off that energy? Fission it. No. What are used in the control rods? So what are control rods? Again, straight definition, cadmium, boron, water and concrete. Well, this is shielding. That's a coolant. Graphite. No. The purpose of high-density concrete in some nuclear reactors. Concrete is a part of the shielding. And finally, in which component of a fission reactor is cadmium used? Again, straight definitions, cadmium is a control rod. So again, nuclear power plants are not found on the regents, but you might find them on some of my assignments. Hope that helps, folks, and thanks for watching. Take care.